Why Angkor automatic grid suffer fatal gridlock. In aviation, when a complex system suffers a total hull loss, we look for the black box. We look for the data that explains why a machine designed for stability suddenly decided to tear itself apart. Angkor wasn't just a city, it was the largest automatic hydraulic processor of the pre-industrial world. Thousands of kilometers of interconnected canals and massive reservoirs, barrages working in a synchronized loop to feed 1 million people. Then in the 15th century, the grid went dark. For decades, we have blamed war or religion, but today we're performing a forensic audit. We're applying the 71 method, a modern systems analysis of the Khmer agricultural cycle to these ruins. We're going to prove that Angkor didn't just fail, it suffered a catastrophic kinetic failure. It was a victim of its own over-engineered feedback loops. This is the crash investigation of the Angkorian water machine. The 71 method audit. So understand the OS, that is the operating system, and the Khmer Empire, that was the 71 cycle. 71 refers to the days of the intensive rice growing season. But more importantly, it represents the timing of the moon sign. The grid was designed to capture 100% of the wet season data. The water in the catchy, it in the barrages for the dry season. In a stable system, this is a perfect loop, but as the city grew, the engineers made a fatal administrative error. They scaled the hardware without updating the agriculture or the architecture. They built more canals, more manifolds, more spillways, but they kept them all locked into a rigid, non-negotiable schedule. See, by applying modern systems analysis, we can see the lag. So every new canal added noise to the system. The water had to travel further through more gates, with more friction. The 71 method audit shows that by the late 1300s, the time it took for water to reach the southern fields was starting to exceed the duration of the cycle itself. The system was lagging behind the climate. Section 2, Manifold Bottlenecks and Throughput Failure. Now, let's look at the hardware. Every hydraulic system has manifold points where flow is distributed. In Angkor, these were the great stone spillways. But there's a ghost in the machine. Silt. In a high throughput grid, sediment is packet loss. So as the Angkorian engineers push more water through the grid to feed a growing population, they increase the velocity. This pulls massive amounts of sediment from the cooling hills directly into the central processing units, the city core. So we have identified the manifold bottlenecks. Over decades, the silt didn't just slow the water down, it throttled the grid. The canals began to fill from the bottom up. Imagine a computer's cooling system where the fluid is turning into sludge. To compensate, the engineers did the only thing their code allowed. They built higher embankments. They tried to overclock the system by forcing more pressure through the silted channels. But this created a lethal feedback loop. You see, higher pressures meant more erosion, which meant more silt, which meant more throttling. The grid was no longer a processor, it was a trap. Section 3, the seasonal reboot failure. Okay, So every system needs a reboot, a moment to clear the cache and reset. For Angkor, this was the transition from the dry season to the wet season. Now, in the early years, the grid was flexible. So if a canal is breached, there was enough redundancy to reroute the flow. But by the 1400s, the grid was too rigid. So it had become a tightly cooped system. So in systems engineering, tight coupling is a nightmare because a failure in one node propagates instantly to every other node. Then came the climate stress test. You see, tree rain data shows us that the 14th and 15th centuries were hit by erratic moon suns, years of extreme drought, followed by mega floods. So when the mega floods hit the throttled, silted manifolds of Angkor Wat, the system couldn't reboot. The water didn't flow through the canals. It flows over them. This systematic desynchronization, the timing of the gates didn't match the volume of the water. The grid blue screen. So massive bypasses were carved out by the water itself, literally deleting entire sections of the infrastructure. This was permanent data loss. Once the main canals were breached and the barrages were bypassed, there was no undo button. You couldn't just repair a wall. The entire landscape had to be reformatted by the flood. Conclusion? Black box. So what did the black box tell us? It told us that Angkor Wat didn't collapse because it was weak. It collapsed because it was too optimized. It was a rigid hydraulic processor that lost the ability to adapt to noisy data. The Angkorian water machine suffered fatal gridlock because its engineers prioritized throughput over resilience. They built a system that worked perfectly until it didn't work at all. And when we look at our own modern grids, our power lines, our fiber optics, our automatic supply chains, we should remember the audit of Angkor Wat. Every over-engineered feedback loop carries the seed of its own kinetic failure. The ruins of Angkor aren't just monuments to a lost religion. They are the physical remains of a crashed system. And the 71 method reminds us, if you can't reboot your grid when the environment changes, the environment will eventually delete the grid for you. Audit complete.